Hey guys, this is Mrs. Keith, and this is the lesson 10 over logarithmic expressions. We are going to remember a few things such as basically how to go back and forth between a log and an exponential function. This is what a log function looks like. This is what the exponential function looks like. Basically, when you have a log, you have a subscript that we call a base that's right here, and then we have the argument right here. It's a lot of times in parentheses. And then it equals the exponent. The reason why we have logs is because they undo the exponent on an exponential function so that you're able to solve one of those. So to convert it from a log to an exponent on the exponent function, you have a base, and then it's raised to an exponent, and it will equal the argument. So you can go back and forth between an exponential function and a log function in order to solve them. So right here, if we need to solve for the argument, we convert it to an exponential function. When you need to solve for an exponent, you change it to a log function. These are some basic rules written below that you need to remember. Basically, if you take the log with any base, and the argument is 1, then your result will be 0. So if I say something like log base 5 of 1, well, that's going to be 0. If I have log base 3 of 1, that's going to equal 0. This one down right below it, that's technically log base e whenever we say ln. So if it's log base e of 1, again, it's going to be 0. Anytime your base is the same as your argument, then the result is 1. So let's say we have log base 5 of 5. That's going to be 1. Or in this next case, log base e of e. That's going to be 1. Anytime you have a base and the argument are the same and it's raised to an exponent, then that exponent will be the result. So let's say you have log base 5 of 5 squared. That answer will be 2. Or if you have log base e of e raised to the 4th power, that's going to be 4. Anytime your base is raised to an exponent and that exponent is a log and its base is also the same as this base. So let's say you have like 5 and then log base 5 of 27. Then that result would be 27. In this next case, we have e, but it says natural log, but that's understood to be log base e of, let's say, 15. Then that result would be 15. All right, so those are just some rules that you need to know. Let's move on. All right, some other rules are things that you need to know is how to convert a log back and forth, a log to an exponential function, and then be able to go backwards as well. So your base will be the base for your exponent. The log is always equal to the exponent, so that will be 3 right here. Basically, what you're saying is this log is raised to that 3, and it will equal 8. Here we've got 3 raised to the 1/2 power, and that equals the square root of 3. Here we've got 5 raised to the -2 power, and that's the same thing as 1 over 25. Here, this doesn't have a base written, so when it's not written, it's understood to be 10. And so 10 raised to the 1st power equals 10. On this next one, we've got 6 log base 6. Again, that base matches this base, and so this will be my result. But you could rewrite it even. You could say log, and then this base right here would be 6. Remember, the log is always equal to the exponent, which is right there, so it's going to equal that log base 6 of 11. And then this exponent right here, this argument right here will go right here. So you end up seeing that they're exactly equal to each other. All right. We can also go the other direction, and we can convert an exponential to a log equation. So when we have 4 cubed equals 64, I can write it as log, and then my base will be 4, and then the 64 will go here. The log is always equal to the exponent. Here we have log base 9, and that's 729. Again, the log is always equal to the exponent. Here we've got log base 2 of that 1 over 32. And again, it always equals the exponent. On the next one, we've got log base 64 of 8 equals that exponent. On the next one, we're going to convert, well, we've already done that. Hang on one second. Well, I was thinking we'd already done it, but we haven't done that. So here we've got 5 raised to the third power equals 125. Again, 5 raised to that third power equals 125. Here we've got this base of 625 raised to the 1/4 power. That will equal 5. Here we've got the 1/2 raised to the -6 power. It's going to equal 64. On this one, we've got 2 raised to the -5 power equals 1 over 32. So that's converting logs to exponential forms. Okay, like we said a while ago, anytime that you have a log and it doesn't write the base, it's understood to be a base 10. So here we've got log base 10 of 100. Well, that's the same thing as saying the number 2, and that's because 10 raised to the second power is 100. And if you're not sure how to do that, you can just say log base 10 of 100 equals x. You're raising 10 to some power, and it's going to equal 100. And then you should know that 10 squared equals 100. So the answer here would be 2. On this one, we're raising 10 to some power, and it's going to equal the square root of 10. Well, the square root of 10 is the same thing as 10 to the 1/2 power. So because these have the same base, this answer right here, instead of it being x, it's going to be 1/2. So that answer there is 1/2. On the next one, we've got log base 10. I'm going to rewrite that 1,000 as 10 to the -3. Well, that equals something, so we need to figure that out. 10 raised to the x power equals 10 to the -3. So this answer is just -3. Now notice here, this is the same base and argument. So that's the same thing as saying 10 to the first power, which is the number 10. So this is the same thing as saying 10. All right, let's move on. This next part is just plugging these into your calculator. The log button is on the left-hand side of your calculator. So let's see, if I plug log of 34.5 in my calculator, I'm going to get 1.5378. If I plug in log of 0.43, I get -0.3665. And if I plug in log -3, I'm going to get an error message. The reason for that is that when you do a log, if you think, well, one thing you should probably remember from algebra last year is that you have a vertical asymptote on the y-axis right here. When you do a log, you have a log graph. You have an x-intercept right here at 1, 0. And you're going to approach that vertical asymptote right there, go through that x-intercept, and then it looks something like this. So my point is that all of this right here is just blank. You don't go past this vertical asymptote right here. So your domain for a log function is x is greater than or equal to 0, or we could say 0, not greater than or equal to. I'm wrong about that, sorry. It's just greater than 0. So it's all 0 to infinity. So what that means is that you can't take the log of a negative number. That's why we got an error message. I'm going to write that. Can't take the log of 0 or a negative number. All right. Okay, on this next section, they want you to be able to evaluate these without using a calculator. So what you should be thinking is, what power do I raise 2 to get 32? Well, that answer would be 5. So this is equal to 5. On the next one, I'm thinking, what power do I raise 49 to get 7? Well, I know I take the square root of 49 to get 7. So that means that the power I'm raising it to is 1/2. So this answer would be 1/2. What power do I raise 1 over 64 to get 4? Well, 1 over 64 is the same thing as 4 to the negative 3. And we've got that x attached there. And that equals 4 to the first power. Well, I want to know, basically, I can set those equal to each other because these bases are the same. So a negative 3x equals 1, which means x equals a negative 1/3. On the next one, we're thinking, what power do I raise 5 to get negative 25? Well, this is going to give me another error message because I can't, again, have a negative inside of a log function. So this is, I guess I should just say no solution there. I was about to say error, but that's just really no solution. All right, using your calculator to find these answers, I'm typing in log base 3. What you can do on your calculator is say math, alpha math, and that will allow you to do a log with a different base other than 10. So like here we have, what it'll do on your calculator is it'll say log, and then you'll have like a blank space there and a blank space there, and you can type in the 3 and the 15. So when you do that on this one, you'll get 2.4650. On this one, you'll get 2.9290. On this one, you'll get negative 2.0272. And on this one, you're going to get 5.2694. On this next part, it's saying use the order of magnitude to compare and like quantities. Okay, so on these, if you were to type this into your calculator, you're going to get that it's 1.477. If you type in this one into your calculator, you're going to get 2.477. The next one, you'll get 3.477, and then all the way up to this one here, and you get 10.477. Now, if you'll notice, each of these, the integer part of these numbers, the integer part, remember, is in this case, the 1, the 2, the 3, the 10. Those are the integers. The integer parts are 1, 2, 3, 4, and then all the way up to 10. Now, where those numbers came from are, this is understood to have an exponent of 1, so it came from these numbers right here. The decimal part has been the same throughout, so it was 0.477. It actually goes on a little further, but I only wrote that much of it. So how many orders of magnitude greater is 3 times 10 to the 10th, then 3 times 10 to the 1st? So the way I would think about this is, if I want to know how much bigger this is, I'm going to divide it by this. Now that's understood to have an exponent of 1 right there. Those 3's are going to cancel out. I have the same base of 10, and remember when you do division, if you remember your order of operations, PEMDAS, you are dividing right here. That's what this line means. So we're on this level of operation right now. But your exponents do one step less, so we're going to subtract them. So we've got 10. We've got exponents of 10 and 1, so I'm going to subtract those. So this is 10 to the 9th greater. When it says how many orders of magnitude greater, it's 9 orders of magnitude greater. All right, on this next problem, this is the word problem. It has the intensity levels of 2 earthquakes measured on a seismograph can be compared by this formula right here, where M is the magnitude given by the Richter scale. How many times more severe was the 2001 earthquake in India that had a magnitude of 7.9 than the 99 earthquake in Athens, Greece, that has a magnitude of 5.9? Well, I'm going to plug all of that into that formula. So we've got the log of intensity 1 over intensity 2 equals magnitude 1, which is 7.9, minus magnitude 2, which is 5.9. So we get the log with those intensities equals 2. Okay, so if I were going to solve this, I want to get this out of the log. Well, the only way to get that out of the log is to convert it to an exponential equation. So right now this is understood to have a base of 10. We're going to take that base and raise it to the second power, and it will equal those logs. So we would say that the earthquake in India is 100 times greater, because that's what 10 squared is. Greater than the earthquake. Oops, I don't know what I was writing there. In Greece. Another way you could say it is that there's an order of magnitude of 2. All right, let's do another example. All right, on the next example, we're going to compare acidity with the pH scale. We've got, we have a pH scale where pH equals a negative log of hydrogen, or hydrogen ion concentration. So using our formula that we have up here, the scale ranges from 0 to 14, where 7 represents neutral, and each whole pH value below 7 is 10 times more acidic than the next higher level. So balsamic vinegar has a pH of 2.4, and a box of baking soda has a pH of 8.4. What are their hydrogen ion concentrates? So first, let's do it for vinegar. And we've got pH. Oh, they told us the pH, sorry. The pH for vinegar is 2.4, and that equals a negative log. And we're trying to solve for the hydrogen ion concentration. So again, this has a base of 10. So 10 to the 2.4. Actually, let me do something real quick. I need to divide by this negative first. So negative 2.4 equals that. Log base 10 of H plus. Go ahead now and convert it. So 10 to the negative 2.4 equals H plus. So that's the hydrogen ion concentration for vinegar. The soda, working out, we would get 8.4 equals a negative log of that. I'm going to divide by the negative. That has a base of 10. So convert it, I get 10 to the negative 8.4. Oops, I made that really big, sorry. 10 to the negative 8.4 equals that hydrogen plus. All right, so how many times greater is the hydrogen ion concentration of the vinegar than the baking soda? Well, 10 to the negative 2.4 over 10 to the negative 8.4. Again, I have the same base, so I'm going to subtract those exponents, which gives me 10 to the 6th power. So this asks for the orders of magnitude. It's just that 6. So it's 6 orders of magnitude greater. Oh, I am not writing very well today, sorry. All right, so those are our notes for today. Thank you.